In this talk, we're going to try to go beyond the techniques from we saw last time. So last time was basically trying to get you all up to speed with like what had happened in quantum rewinding, starting from mid-90s when someone first realized that it was a problem at all, to 2016. Where by 2016 we had these techniques to argue proof of knowledge in kind of a weak sense, and also fully handle zero knowledge for a limited class of protocols, like basically these like 3-message commit challenge response protocols. But since then, the last few years, there's been a lot of work showing that you can go far beyond these original protocols, these original techniques. So this talk is going to just focus on one of these new techniques that has, since this paper was written, also found other applications and beyond what I'm going to talk about today. So I'll mention that very briefly at the end. Okay. All right, so last time, we saw how to use Unruh's one-bit rewinding lemma to show that when you instantiate Blum's protocol with collapse-binding commitments, you get a post-quantum proof of knowledge. So this technique has some drawbacks that we saw last time. We get weaker than expected security, right? We can only start extracting once the prover convinces the verifier with probability 1/√2 plus epsilon. And it was unclear like where that comes from. Right? And perhaps a more serious issue that doesn't show up when you're just looking at the Blum protocol, but shows up when you're wondering like, more generally about like, what classically secure protocols you can prove post-quantum secure. You realize that this technique, while it can be extended a little bit, doesn't go too far and doesn't handle a lot of protocols that you really ought to be post-quantum secure. So for instance, the GMW graph 3 coloring protocol is one protocol that this technique doesn't work for. Okay, so we're going to see a more powerful rewinding technique that's going to allow us to prove soundness and zero knowledge for a much bigger class of protocols. So this talk is not going to be about zero knowledge. So last time I talked about both proof of knowledge and zero knowledge rewinding. Both are called rewinding, and actually I think people find this a little confusing. That like why haven't we solved rewinding? Doesn't Watrous done it? That there's just many different problems that are called rewinding, or many different tasks that are called rewinding, and we're going to focus on the class of tasks that come from like doing proof of knowledge techniques. So trying to record lots of responses from a prover. Okay. All right. So our motivating example throughout this talk is going to be Killian's succinct arguments protocol. So I'll show this protocol. Don't worry if you haven't heard of this before. And we're going to talk about why is post-quantum security of Killian's protocol like, particularly difficult. Like what makes this more challenging than something like Blum? And then we're going to show how to handle the post-quantum security. So it's going to be a new technique that allows us to rewind a quantum attacker many times. And there's going to be several components to this that we're going to cover. Okay, so succinct arguments. A succinct argument is an interactive protocol between a prover and a verifier, maybe non-interactive. So as usual, the prover is trying to convince the verifier that some statement is true. But this time, instead of asking for something like zero knowledge, we're going to ask for a different property. And maybe this one might feel a little less cryptographic. The property we want here is just that the verifier can be really efficient. So that means that the total communication between the prover and verifier is very short. So the communication verifier efficiency has a polynomial dependence on the security parameter, but the dependence on the size of the instance, x, and the witness, w, is polylog. Right, so compare this to the trivial protocol of just sending the witness to the verifier. This is exponentially more efficient. Right, so it's saying if I have like some massive claim, I can just send you, we can just communicate like a few bits back and forth, and you can be convinced that this claim is true. Okay. It turns out to get succinctness, you need to relax your soundness property a little bit to mean an argument. So this just means that the soundness holds against only efficient cheating adversaries. So there are going to be like information theoretic or like exponential time malicious provers that could fool the verifier. But as long as the prover is constrained to be efficient, there is not going to be a way to cheat. And cheating here means convincing the verifier on a false instance. Okay, so the canonical construction of succinct arguments is due to Killian from 1992. So Killian showed that there is a 4-message succinct argument protocol for any NP language, assuming just the existence of collision-resistant hash functions. So this is a relatively mild cryptographic assumption, a little stronger than one-way functions, but there are much, much stronger assumptions out there that we make. And this has many, many applications, both in theory and in practice. So theory applications like universal arguments and zero knowledge, but it's also made its way over to practice. So you've heard of like snarks, ZK snarks, things like that in blockchain. Succinctness is really important, and that really came out of this idea of Killian. Okay, so extra motivation for focusing on this, like beyond the fact that we think succinct arguments are just important inherently, the reason we care about them from the quantum rewinding context is that studying succinct arguments is going to force us to develop general purpose techniques. So what I mean is that typically, like the way that we prove soundness, right, is we're going to record several transcripts and use that to specify a witness. And by the very nature of the succinct argument, we have to record a lot of transcripts to get a witness, right? Each message is really short. It's like polylog the witness length. So if I want to record transcripts from the prover and record it and get a witness out of that, I'm going to need a lot of transcripts. So in that sense, in terms of like how much I need to extract from the prover, this is kind of the hardest case of quantum rewinding. Right? I need to do lots and lots of rewinding. Like last time, I only needed to do basically 1 rewind. I needed to get 2 transcripts from the prover before I could get my witness. Here, because the prover gives me so little information, I need to rewind it many, many times. So basically, if we focus on rewinding this, we're going to have to develop techniques that will be much more powerful and much more general. And the techniques we end up giving for this will give you much better guarantees, even in simpler cases where you only need to rewind the prover a few times. So that's the main reason for just looking at this example today. But we shouldn't. My general claim here is that we shouldn't like focus too much on like the particular example of succinct arguments. It's really just like a testing ground for our techniques. Okay. But with that in mind, let's look at how Killian's particular protocol works. So the idea behind Killian is to take any probabilistically checkable proof system and turn it into a succinct argument. So a PCP is just a highly redundant way of encoding an NP witness, right? It's some way of writing down a witness such that if there's any error in this proof, that this error is propagated to many different locations in the proof, and you could detect this by just checking a few positions. Okay? So you might be wondering, like, why isn't one second. Sorry. Might be wondering why a PCP isn't already a succinct argument, right? After all, it has this feeling of like, well, the verifier is only checking a few bits, so isn't this a succinct argument? Right. The problem is that this isn't actually a way for a prover to convince a verifier. Like if the verifier doesn't trust the prover, then this model breaks down. Right? This PCP model is assuming that the prover has written down the whole proof somewhere, and that the verifier is just coming by to look at a few positions. Right? But if the prover is untrusted and the verifier doesn't want to communicate many bits, and the verifier is just like, well, prover, tell me what is at the PCP in these positions, the prover will just say whatever the verifier wants to hear. Right? So the soundness of this PCP system doesn't give you, it doesn't really map onto like a scenario in which the prover and verifier are interacting and the verifier doesn't trust the prover. Okay? So Killian's protocol throws cryptography onto this setting and turns it into a secure interactive protocol. Where now you don't have to make any such modeling assumption. Okay, so how does it work? The main idea is to have the prover commit in advance to the PCP. So very simple in hindsight, but it's a special kind of commitment that makes this work. So in the original protocol, what the prover and verifier do is the verifier samples some key, some description of a collision-resistant hash function and sends it over to the prover. And the prover uses this hash function to do a Merkle tree or tree commitment to the PCP. So what that means is it's going to take its PCP and basically divide it up into the leaves of some binary tree. And then it's going to hash its way up this tree. So every single internal node of the tree is going to be computed by applying the hash function to its 2 children. Right, so let's just say the hash function maps 2 lambda bits down to lambda bits. right? So I can hash these down to lambda bits, and then I can take 2 consecutive blocks of lambda bits and then hash those again, right? Go up another level, go up another level, and finally, when I'm down to lambda bits at the root, I send that over as the commitment. And a nice property of CRHFs is that they're composable, so this overall thing is a CRHF. But not only that, we actually don't care too much about this overall hash function that's hashing the whole PCP to this small root. We really care about the fact that this has a nice property that I can actually open this hash function, I can open these commitments without having to reveal the whole PCP. That is what this structure is buying me. So once I get that commitment done, the verifier can run a PCP check. So it can send some random coins specifying some positions it wants to see. And now for any position the prover wants to open up, it can send a short proof of opening. So if it wants to reveal this, the colors are a little bad, but if it wants to reveal this black square right here, what it can do is it reveals the values of all the siblings on the root to leaf path, right? So in particular, it's revealing the value of this without having to reveal the entire set of leaves for this tree. Instead, it just reveals some polylog number of bits, these here. And this way, the verifier can hash its way back up the tree and just check that this corresponds with the root. So that is the key property of these tree commitments, that there's a way to do succinct local openings to any position. Okay. So in the end, the verifier will accept if the PCP verifier is convinced and all these openings are valid. So the intuition of this, I think, is pretty clear, right? We're trying to run a PCP check, and intuitively, this hash function or this tree commitment is forcing us to commit in advance of the PCP, and we just shouldn't be able to change our mind based on what the verifier wants to see. But how do we formalize this and actually prove security, right? Well, unsurprisingly, it's going to be by a rewinding reduction. Right? So this is the classical security argument for Killian's protocol, which surprisingly isn't in the literature anywhere. I learned this from a set of lecture notes, but Killian's original protocol just said that it works. So fun fact. Okay. We want to show that this CRHF is really forcing the prover to respond consistently with some PCP string so that we can invoke the soundness of the PCP system. I have a question? Yeah.
Could you go over that tree again? I also see that the colors are a bit different on the screen.
Yeah.
Is he committing to the entire tree and then?
Good. Okay, yes. So the goal is, the prover, this is the PCP. The PCP is supposed to spread over all the leaves of the tree. And the prover wants to commit to the whole PCP in advance. This is what the honest prover is supposed to do. But in the actual protocol, the verifier is not going to ask to see the whole tree, because crucially, succinctness is only going to happen if I only look at a small part of the tree. So the verifier is only going to ask to see a small part of the tree. And this tree commitment structure allows me to commit to the whole thing, but then only reveal a small part of the tree. And the proof that I'm opening this small part of the tree correctly is very short. It's together, it's much shorter than the whole tree. So I think it's hard to see how amazing the savings is when it's only 4 layers. But if you imagine a huge tree, it could be very long at the bottom, but you only have to send a polylog length opening to certify any position. Does that answer the question?
Yeah, the opening is just on the bottom.
Or the opening for this black square is these squares, these blue ones here, right? These are the ones that allow me to compute this hash, go up to here, right? These blue things. I just need to compute these hashes. Once I'm here, I don't need these two, I just need this node here, right, to go up. Yeah. Okay, so how do we show that this protocol is actually doing something? We're going to argue that by rewinding the prover many times for the last 2 messages. Okay. I think I forgot to mention that today when we talk about PCPs, let's think of them in this negligible soundness regime. So we'll think of it as the verifier is going to ask to see some polylog number of bits. And if it's a no instance, then there's a negligible chance that the verifier will accept. Okay, so I know that PCPs can have constant soundness error, but we're going to parallel repeat the queries. and get this in a regime where I'm still looking at a small number of bits, and the soundness error is negligible. Okay? So when we're doing security, we're saying, well, I'll assume I have a classical malicious prover who is convincing me with some noticeable probability on a false instance, and I want to get some contradiction. So here's what's going to happen. I will repeatedly query the prover, I will run this prover through the first two messages of the protocol and fix some prefix to this transcript. So I'll fix some CRHF and some commitment. And then the last two messages I'm going to keep repeating. So what I do is sample a random RI each time, ask the prover to answer me. It gives me some ZI. And every time it answers correctly, I'm going to record that. And what's going to happen when I piece together all of these accepting transcripts? Well, I claim there's really only two possibilities. Right? Either all these transcripts are consistent with each other. Right? So notice that each transcript, each ZI, it's going to fill in a little part of the PCP. Right? So as I amass more and more transcripts, if they're all consistent with each other, eventually I'm going to piece together a PCP, or most of a PCP. And what's going to happen in that case is that I'm going to get a PCP that basically describes how my prover is answering me. And if my prover is convincing with some noticeable probability, then I'm going to get some impossibly good PCP if the answers are all consistent with each other. Okay? Like this PCP is as good as the prover, but we're claiming the prover is too good. This is a false instance. So there is just PCPs are information theoretically sound. There is no PCP that is this good. So the only other option is that the transcripts that I get across all these different rewindings are inconsistent with each other. And the awesome property of the Merkle tree is that anytime you have any inconsistency, that means that you're going to violate collision resistance of H somewhere in the tree. So you'll have to take my word for that if you don't see it immediately, but you could write this out and see some examples. That anytime there's a collision, it has to be explained by a collision at some H. So now might be a good time to make questions. If this is your first time seeing this. Maybe thumbs up, thumbs down? OK, great. So the important detail to remember here is that we really, as we did last time, only care about the last two messages here. Right? We kind of have some transcript that's fixed for all time. We stop caring about it. And we're just going to think about asking the prover a question, getting its answer. And our goal is to record lots of accepting transcripts. And then the rest of the reduction takes care of itself. Right? We've already argued that once you have enough accepting transcripts, then you'll get your contradiction, either the information theoretic contradiction or you break the computational assumption. OK, so so why is post-quantum security difficult? I sort of already alluded to this one, but let's just do it a little more formally. Remember last time we had this rewinding template that said the way that you prove something as a post-quantum proof of knowledge or post-quantum sound is you want to combine two ingredients. First, you want some sort of collapse binding commitment, and this reduces your problem to recording the adversary's response. It's reduced to recording this one-bit decision of did the adversary succeed or fail on this query. And we combine this with this one-bit rewinding lemma that says, well, this is a slight generalization of Unruh's lemma due to DFMS that generalizes it to larger constants. So last time we plugged in the d equals 2 case, and we said the probability you succeed twice is p to the 3. But in general, for a constant d, it's p to the 2d minus 1. And actually, this turns out to be tight. So step 1 is not the issue here. So technically, we didn't see any collapse binding commitments anywhere, but there is essentially an analog of that for hash functions. And as long as the CRHF in Killian's protocol satisfies this notion of collapsing, which is just a security property that says that recording the adversary's response will be indistinguishable from recording this one-bit decision. I lost my train of thought, but step 1 just works if you plug in the right notion of a CRHF, and it's not hard to construct this object. So collapsing hash functions exist from a wide variety of assumptions, including learning with errors. Okay, so we're not worried about that step. What we're really worried about is this 1-bit rewinding, right? You're paying attention to what this value is. When d is larger than a constant, this is not going to be a meaningful expression, right? P is going to be some noticeable function. This is the prover success probability. And so this is only going to be noticeable when d is constant, right? And we don't just need d to be super constant. We need it to be an arbitrary polynomial. So we have to do like much, much better than this. And in fact, you can show this lemma is tight, that there is an example that actually like achieves this like exactly. So whatever we do is going to have to do something else. It's going to have to deviate from the rewinding template where we were just kept repeatedly querying the prover. Because you can show that actually you're never going to get enough accepting transcripts if you just do that. So the way we handle this is with a different, like a totally different template for rewinding. And so let's see what that is. So here's the setup, right? The initial setup that I have some prover. I've run it on some random challenge, and I've recorded this 1-bit disturbance of whether it accepted or rejected. And instead of just going to the next query, let's see what's happening here, right? The issue is that the success probability of this prover could have dropped, right? You have some new prover state S prime, and the worry is that its success probability can be much smaller than your initial prover success probability, right? And when I said that Unruh's lemma is tight, what can happen is that you can have an example where the success probability just degrades like exponentially fast. It goes like 1/2 to 1/4 to 1/8 to 1/16 and so on. So we need some way to address this problem, that the success probability is small. And it's going to look very obvious in hindsight, but the way we do this is we write down a procedure that will fix this problem. We're going to write down a repair procedure whose only goal is to output some new prover state whose success probability is close to p again. So I want to emphasize that what this is not doing is it's not repairing you back to the original state. It's not, S1 is not S. Okay? The original state could be information theoretically lost. What it's doing is it's giving you a different state that has the same property of S, in that they both have roughly the same success probability. And the observation here is that this rewinding that what our reduction needs is just to preserve the success probability of the prover. We don't actually care that our prover is sort of changing from step to step to step. As long as every single time I ask the prover a question, I have a p probability that it answers me correctly, then I'm still going to obtain enough accepting transcripts, and I'm still going to either get a consistent PCP or a collision in my hash function. So I don't actually care that the prover is changing from step to step as long as its success probability stays the same. And so that's why it's going to be enough to only repair success probability. Okay, so the rest of this talk is going to be like, where does this box come from? Like, how do we implement a procedure that takes you from this state where things have been disturbed and bumps you back up to a state that has good success probability again? So I think I'll just dive right into it. So the state repair task is you're given S prime, this state after a 1-bit measurement has disturbed your initial state, and my goal is to output a better adversary. And we're going to use this Marriott-Watrous alternating projectors idea that we actually saw in the last talk for zero knowledge. So sort of to Chris's question, like, where are we going to pick these projectors? Like, what projectors could possibly help us with the task at hand? So let's look at what we did last time and see if that can give us any inspiration. So last time when we had this Watrous rewinding task, we were given some verifier state psi and some projector pi g indicating successful simulation. And our goal was to output some particular conditional state. And the algorithm we came up with was to alternate two projectors back and forth, pi 0 and pi g. Why these projectors? Well, pi 0 was chosen to contain the state we started at. Right? The state we started at was psi tensor with a whole bunch of zeros on some ancillas. And pi 0 is this projector that says, like, this is characterizing where I'm beginning. Okay? It was kind of a stand-in, actually, for a projector onto like the exact state psi, which we don't know. right? This is sort of the best thing we have. This is like some non-trivial projector that contains my initial state. And my goal was to output a state in the image of pi g. And so I alternated this with this other projector that contains my target state. And so with this like high-level intuition of like one projector should contain like where you're currently at, and one projector should specify where you want to go, how would we design two projectors? How do we pick two projectors that are going to solve the state repair task for us? So, okay, I think even with this, it's not so clear. But let me make a huge oversimplification that may make it a little easier. So let's say that we could efficiently implement some projector, pi p, some binary projective measurement onto pi p, where the image of pi p exactly corresponds to adversary states that are p successful, that have like p success probability at least. Okay. At this point, it should be a total mystery where this comes from. Like, why is this even like a well-defined subspace? But like, let's just ignore that for a second. Let's pretend that this is reasonable to do. Let's say we had this, okay, and we could efficiently implement this projection. Like, if we had this, how could we repair the state? Well, the point is that this projector says where we want to go, and we also know a projector corresponding to where we are right now. Right? So let's just say that this outcome was 1. Then where we are right now is we're in the image of pi r. Right? So I'm going to alternate the pi r and pi p measurements until pi p accepts. So what the repair step looks like is after this initial disturbance where I've applied pi r and gotten s prime, I would just measure pi p, measure pi r, measure pi p, and just keep doing this. 3 is just an example. It could go as long as it needs to go until pi p accepts. And because this is a projective measurement, when it accepts, I know that I'm in the image of pi p. And just by the way I defined pi p, if I'm in the image of pi p, I am at some p successful state. So this, yeah?
I want to ask because in the end, when you want to abstract, you're going to need more than just a single bit indicating acceptance or not.
Yes.
Are you going to handle that the same way using Untitled lemma, or?
No, it's good. So good question. So here, when I do this disturbance, right, I'm actually assuming it's accepting. So here, I would also do this measurement of the message. And what I'm claiming is that I'm actually going to ignore that measurement for this analysis. Okay, but I'm going to say, like, if this procedure like works in this case and doesn't work when that measurement happens, then that would be a distinguisher. Like this overall like reduction, like because these steps hopefully are efficient. Like if I'm writing down an efficient reduction, then anything like whether or not it succeeds will still hold whether or not I do this measurement. So that's how I'm going to like insert this measurement for free here. Yeah. But that only works for efficient reductions. So. Did everyone understand my answer to John's question, by the way? That's kind of, I'm not going to go back into it, so just want to make sure that that point makes sense. But, because I'm using, so I'm, good. So the question was, why does this only work for efficient reductions, right? Why does the argument I just gave? And because I'm using the security of the collapse binding commitment against the reduction itself. I'm saying that if the reduction worked in that like it successfully say, like, let's say that when I only measure 1 bit, I will have pi p accept within like 100 steps, right? And somehow, and let's say that when I measure the message, in addition to measuring that bit, I no longer have pi p accepting within 100 steps. Then that means that this reduction that runs for 100 steps and sees whether or not it got back to pi p is a distinguisher for the collapse binding property. So if this reduction is inefficient, then I haven't contradicted the property.
Okay, but here all the things are efficient.
Because of this oversimplifying assumption, yes. So in this toy example, yes, everything would be efficient. Or I guess I haven't even shown that for the toy example yet. But if it were, then yeah. OK. Could I get some thumbs up, thumbs down indication of whether I should move on? I'm also very happy to stay here. I think these are great questions. So Please don't be shy about asking questions. It's only going to get worse, so. OK. All right, so I haven't explained several important things. So first off, even in this toy example, I actually didn't convince anyone that this was efficient, right? So why does this actually terminate? It could just be that you alternate these things back and forth, and pi p never accepts, right? So why is this going to work? And then the second piece was, where does this pi p come from? I think that's the more mysterious part of this. But let's handle one first. So why does this terminate? Well, last time we had alternating projectors, we also had to understand why alternating them back and forth would eventually terminate with one projector accepting. But the way we did that last time, if anyone recalls, is we used very particular properties of those two projections to say that they would eventually terminate. Namely, that when you looked at their Jordan subspace angles, like all those eigenvalues were 1/2. And we used that property, that we could understand those Jordan subspace angles, to say something about how long it would take to alternate them back and forth. And in this case, we have no such guarantees about pi r and pi p. So we really have no idea what pi p is. They just defined it. So we have no idea why pi p and pi r should have angles that are well behaved in any sense. And indeed, they really don't. And yet, there is a way to analyze how long this is going to take. And the trick is actually to not analyze just this repair procedure itself, but to analyze the running time starting from before you even disturb the state. So there are alternating measurements that happen, like pi p, pi r, pi p, pi r, pi p, in the repair procedure. But there was this one measurement that happened before the repair procedure, which was a measurement that took me from a good adversary and disturbed the state. This is the measurement corresponding to querying the adversary for the reduction. Right? So in terms of their role in the reduction, this initial pi r is very different from all these other measurements. But if you think of them as just one sequence of alternating measurements, analyzing the behavior of this whole thing gets a lot easier. And the reason for that is that when you're analyzing this whole sequence of measurements, well, you're starting with a state that's in the image of the pi p projector, say by assumption. And what I'm asking is, how long does it take me to get back to that same image? And it turns out that when you phrase the question that way, not about getting from the image of one projector to the image of the other, but saying, I'm going to alternate two measurements back and forth, and I want to ask, how long does it take me to get back to where I started? It turns out that that question doesn't actually care about what the projectors are. So I think it's a little hard to believe, so let's look at our favorite example, which is the 2D case. So in the two-dimensional case, look at pi p and pi r. So here's the state I have before I query the adversary. So I'm here at S. And I claim that if you alternate these measurements back and forth, well, I guess there's two cases to think about. So when that first measurement happens, I either go here to S prime, or I go here to S prime perp. And intuitively, if I'm very far away from S, it's going to take me a long time to get back. Right? If theta is very small, then S prime perp is very close to orthogonal to S. And so it should take me a long time to get back to S. And correspondingly, if I'm at S prime, I'd get back to S pretty quickly. Right? But these differences are sort of canceled out by the fact that if S prime perp is very orthogonal to S, I'd have a very small chance of ending up there in the first place. So if you write out these probabilities, you'll find that actually the running time, or the expected time it takes to get back to S, is just totally independent of the angle. So, and because these running times are independent of the angle in each subspace, you can extend this to the general case by Jordan's lemma. All right, so that's it. That's why this terminates, at least if there are projections. OK, so I think the bigger question is, why do we have a projective measurement that is somehow just checking if your success probability is p? I think that is a very mysterious assumption to make. So the rest of this talk is basically going to be, how do we handle this mysterious pi p? So A different way to think about this is how do we measure the prover's success probability, right? Pi p is supposed to be a measurement that's testing whether or not your success probability is above this p threshold. But let's think about this more general question of how do I even learn your success probability in the first place? And the bad news is we actually can't do this efficiently. And not just that it seems hard to do, but that if there were a general procedure to do this, then I think it would imply that sharp p is contained in BQP. Something. So we really will not expect to write down a general procedure for this. The good news is that even though you can't do it efficiently, you can approximate this to any precision you want, any inverse polynomial precision you want. So I'll say how this is done. It's a technique called alternating projectors, again. Let's see how that works. So to set this up, to set up the success probability estimation, I'm going to think of of running the adversary in a random challenge. I'm going to rephrase that in a more quantum fashion. So instead of picking a classical random challenge, I'm just going to think of that as introducing a separate challenge register R and initializing that to the uniform superposition of all challenges, and then running the prover controlled on that extra register. Okay? So this is an equivalent process. Like if I trace out that register at the end, it's the same as having run the prover in a random challenge. But it's going to be helpful for me to actually keep this extra register around. So I'm going to define plus R to be this uniform superposition over all challenges R. Pi except is going to be the projection that it's going to, controlled on this challenge register, it's going to check whether the prover answers correctly on that particular challenge. And so things are defined so that if I take my prover state S, I initialize the ancilla register to plus R, and I measure this pi accept projection I just defined, well, my probability that this accepts should exactly be the success probability of S. So these are just definitions. Nothing has happened yet. Okay. But if there's one thing to memorize, it's that this pi accept is this definition, that it's the controlled on the challenge register, check whether the prover answers correctly. I'm going to have one other projection, which will be the projection corresponding to where I begin initially. So it's a projection that checks that the randomness register is indeed a uniform superposition and acts as identity everywhere else. And this idea from Marriott-Watrous is that we can learn the success probability of this adversary by alternating these two measurements back and forth. Okay, so what I do is I initialize the state, I alternate these M accept and M uniform measurements back and forth, and I get all these outcomes. And how do I turn this list of outcomes, B1, B2, B3, these binary outcomes, into an estimate for the success probability? The formula is just to output the fraction of times BI equals BI plus 1 occurs. Okay. So if you're paying really close attention to when I was jumping around these two projectors last time, maybe this is already obvious to you, but we're going to just go through an example to make sure this is clear. Like, why does this value, why does this fraction reveal the success probability? Okay, so here's what we're thinking of, right? I have a state psi that's initially in the image of pi uniform. So this is a plus RS. Okay? For simplicity, let's just say that I am in one Jordan subspace. So in general, we can be in a superposition of many different Jordan subspaces. But just for this, let's say that I'm guaranteed to be in one Jordan subspace. Okay? And I initially have some success probability pj, which shows up as the cosine squared of this angle. Right? Pj is precisely the probability this adversary S answers correctly on a random challenge. And my task is, how do I extract pj from the alternating measurement outcomes? Right? And if you sort of just watch how this state jumps around as I alternate these measurements, like every time I do a measurement, what happens is with pj probability, the next measurement will give the same outcome as the previous one. Right? I have pj probability, let's say, going from a rejecting pi unif measurement to a rejecting pi accept measurement. And so every single time, like this, it's like an independent coin flip happens. Right? With pj probability, I stay at the same outcome as before. and with 1 minus pj probability, I flip to the different outcome. And so if I want to recover my success probability, I'm just going to look at the number of times like b0 equals 1 is followed by b1 equals 1, right? Or b3 equals 0 is followed by b4 equals 0. Right? So I count this up. This occurs 6 times. And so I'm saying the success probability is something like 6/8. Okay. And the longer you do this, the more accurate this becomes, of course. So this is OK? Yeah. OK, so in general, though, we don't have to just be in one Jordan subspace. Right? And what happens when your initial state plus R tensor S is contained in different Jordan subspaces? Well, you could have a picture like this. Right? We're no longer in this well-behaved setting from the last talk where all the Jordan subspaces have the same angle. They can all have different angles. And these angles correspond to success probabilities. Right? These angles mean, like if this eigenvalue P1 is 0.15, that means if I were entirely in this subspace, then that would correspond to a prover with that success probability, like 0.15. Right? And a general prover can have a component in this subspace, a component in this one, component in this one. And so its success probability becomes the weighted average of the various success probabilities in each Jordan subspace. So for instance, if I have like alpha1, u1, alpha2, u2, alpha3, u3, my success probability of this prover is just the sum of over pj times alpha j squared, like the probability mass I have in each subspace multiplied by the success probability on that subspace. Okay? So what this is saying is that success probability of a prover is really the average of your different eigenstate success probabilities. Okay? So actually earlier when I defined this projection pi p, it was kind of ill-defined. Like it was not clear like why that was even a linear subspace at all. And this picture makes it really clear what that subspace should be, or what the ideal subspace would be that you're trying to return to. And that would be for any value of p, it would be the direct sum or the span of all the subspaces, all the Jordan subspaces, where the eigenvalue is above p, or is at least p. Right? Good. So a key fact that we're going to need is that when you alternate these measurements back and forth, the outcomes are distributed according to a particular subspace with probability equal to like the amplitude squared that you have in that subspace. So this is a pretty deep fact. Let me just spend like a minute here like unpacking this. Okay, so I'm saying like if I have a prover who, let's say, has a uniform superposition on these numbers are kind of annoying. Okay, let's say I have a uniform superposition on 1/4 success probability and 3/4 success probability. And I alternate these measurements back and forth. The claim is that I'm not going to see something like, well, this prover has success probability 1/2 because it's in superposition of 1/4 and 3/4. But when I alternate these measurements back and forth, I'm not going to estimate 1/2. The claim is I'm either going to get an estimate that's really close to 1/4 or an estimate really close to 3/4. Okay? So it's saying it's going to behave according to one of the subspaces. And the probability that the outcomes are consistent with one subspace is proportional to the weight I have on that subspace. This would be a great time for questions. If people want more explanation for this or less, I can also does anyone want a proof of this claim? Well, yeah, so I run this procedure, and I get this list of outcomes. And I'm saying, like, the estimate I get is going to be either very close to 1/4 or very close to 3/4. Yeah. And yes, yeah.
I guess I don't quite see what you do with that, what you can take from that.
Yeah, that's not obvious yet. we're going to make use of that in a second, but I just want to make sure this fact is very clear first. Yeah?
So basically, if the probability of success is 1, would that just be the same as proven?
If the probability is 1, it would be the same as what?
No result.
I don't think so. But success probability 1 would mean that you're contained on one subspace, right? Because if you have success probability 1, you can't have any weight on lower subspaces, right? All these subspaces have angle between 0, or eigenvalue at least, between 0 and 1. Okay. So I mean, there is a big difference, I'm claiming, between a prover who has success probability 1/2 because all of its weight is on the 1/2 subspace, and a prover who has success probability 1/2 because it's a superposition of a 1/4 and 3/4 success probability prover. I mean, those are like two fairly different objects actually, even though if you just ran it once, you wouldn't be able to tell the difference. But if you ran this estimation procedure, the difference would gradually reveal itself. And indeed, the right way to think about success probability is through this eigenvalue view. So when we say that we want to restore your success probability, we actually want to restore you to being contained in the subspaces whose eigenvalue is above some value, some p. Okay. Is there any demand for proof of why this is true, or is this just obvious? I don't know. Yeah, a little more detail why this is true. Okay, so there's a really nice argument for this that I found in Oded Regev's lecture notes on Marriott-Watrous. And the idea is you imagine doing this sequence of alternating measurements on your state. So you get a whole bunch of outcomes. And then suppose that after that sequence of measurement outcomes, after you're done doing all your measurements, you do one extra measurement. And that measurement measures which subspace you're in. So just because all of these are orthogonal subspaces, there exists a measurement that can distinguish which subspace you're in, right? I can do a measurement and it just tells me exactly which subspace I'm in. So I could do this measurement after my sequence of alternating measurements. And that measurement, the measurement of which subspace I'm in, commutes with pi unif and pi accept. Right? Because there's many ways to see it, but they're all block diagonal on the same basis. So I can measure which subspace I'm in afterwards and actually commute it to the beginning, and that doesn't change the measurement statistics. So that's saying that if at the very beginning I'm in a superposition of different subspaces, I could measure which subspace I'm in, which will collapse me to a particular subspace with probability alpha j squared. And then my resulting measurement outcomes are as if I started entirely in subspace Sj and just alternated back and forth. So the fact that the measurement of which subspace I'm in commutes with with pi unif and pi accept, that is why this behavior emerges. Okay. Yeah.
It's probably silly because I kind of missed something, but this is supposed to somehow be, it's supposed to have a cutoff at some point, right? That here in subspace would probably be greater than a value. Is that something we're implementing here, or it's just estimating how this is?
So you're saying back to the original goal of estimating whether I'm above some value? Yeah, let me get to that. I haven't brought it back to that yet. I'm still just talking very generally about this question of estimating success probability. Right, so good. Let's see. Yeah, so Chris, to answer your question, the way to think about what this procedure is doing, or towards answering your question, is you should think of this alternating measurements procedure as sort of an approximate projective measurement, in the sense that it's approximately measuring which subspace you're in. The longer you run this procedure for, the more you're going to converge to being in one subspace, and the probability you're in that subspace is proportional to the weight you had on it. So really, as you go to the limit, this is just the measurement of which subspace you're in. Okay. Right. So let's make that a little bit more formal. So I'll write down two properties of this Marriott-Watrous estimator that we're going to need. So the first one is just that the expected success probability at outputs is equal to the success probability of my initial adversary S. And the second thing is this is a formalization of this behaving like a projection claim that I just made. So like one defining property of projective measurements is that like when you do them twice in a row, they will give you the same outcomes. And here, something very close to that happens. In particular, if I take any state, S, and I run it through this Marriott-Watrous estimator once, get some estimate P, and then I run it through it again and get some estimate Q, these two estimates are very close with high probability. Right? So if this were a projective measurement, they would be equal with probability 1. But I'm claiming we have some relaxation of this, where P and Q are epsilon close with all but delta probability. And the way that you get these guarantees is you need to set the running time, the number of alternating measurements you do in the estimator, to be polynomial in 1 over epsilon and polylog in 1 over delta. So in particular, you can get to any inverse polynomial additive precision with inverse exponential, except with inverse exponential failure probability. So I think this property was first noticed in a work of Zandri. So he called this property like epsilon delta almost projective. If you're wondering why I've been citing both Marriott-Watrous and Zandri, it's because Mark didn't know that Marriott-Watrous existed, and so when he was trying to solve a problem, he just invented it and then came up with a bunch of names for it. And his view of it turned out to be more useful for what we're doing. So yeah, let's go back to our original goal of rewinding and see how this Marriott-Watrous success probability estimator fits in. So recall in our high-level sketch, right, we had this exact measurement of pi p, which we now have a better understanding of. Right? This pi p should have been all along the projection onto the Jordan subspaces of pi uniform and pi accept with with eigenvalue at least p. But again, we don't know how to implement that measurement, and so we're going to have to replace that with something else. And the obvious thing to plug in is just the quantum algorithm that's going to run the Marriott-Watrous estimator and output 1 if the estimate is at least p, and output 0 otherwise. Right, this seems to be the closest thing we have to this pi p measurement. So can we just plug that in, right? Plug in Marriott-Watrous alternating projectors into a larger Marriott-Watrous alternating projectors algorithm. Basically, like run it on itself. Don't read into this too much. They're really like two totally different sets of alternating projectors, right? This pi p over here is going to, this MWP is alternating this pi accept pi uniform projector, these two projectors back and forth. And this bigger procedure is alternating like that with a different projector here. Okay, so there's like big projectors and little projectors. Okay, so subtle point is, maybe it's been clear through the discussion of the Jordan subspaces, that we're not really just trying to restore success probability. It's not going to be sufficient to do that. We need to restore actually being in the support of these Jordan subspaces where the success probability is at least p. So the invariant we're actually going to maintain is that you're strongly p successful, which is my way of saying you're concentrated, like almost all your weight is concentrated on the eigenspaces where your eigenvalue is at least p. So this is the invariant. I want to start with a state that is strongly p successful, and after disturbing it, I want to repair it to some other state that is strongly p successful. Okay, so this seems pretty promising, but one problem is I kind of lied about having two projectors on, at the outside here, because this MWP is not a projective measurement. I claim that it has some features of a projective measurement in that the original Marriott-Watrous estimator has outputs that kind of look like the outputs of a projective measurement, but in no sense is this formally a projective measurement. Right? And actually, this threshold version of Marriott-Watrous, this version that accepts or rejects depending on if you're above this p cutoff or not, That's actually very, very far from behaving like a projective measurement. Because you could imagine if your state has eigenvalue like exactly p, and I'm running this estimation procedure, it has like a 1/2 probability of landing on either side of being above or below the p threshold, right? So if I run this thing twice, I certainly don't have any guarantees that like my two outputs are going to be close. The binary outputs would be close. I might get 1 once and 0 another time. Right, so this Marriott-Watrous estimator, this estimate and cut off at p, is not a projective measurement at all. So all the guarantees I had about this earlier when I argued that this procedure is eventually going to terminate, that doesn't apply here, right? Because that only applied when I had two projective measurements alternating back and forth. This doesn't fit that template. Okay. Maybe I'll pause for questions here. It's going to get a little bit more complicated. Is there anything that I should say again? I'm really happy to repeat things. Yeah.
Is it obvious that in the initial state, the structure is successful?
Not at all. It's actually not. And I've been lying about that this whole time and hoping people don't notice.
No, but it seems like it should be that much.
Yeah, so there's two ways to handle it. One way is how we did it in this paper, which turned out to be suboptimal, which was just do an initial estimation of the state, and then like you're using that to actually set the p threshold in the first place. And then like you do some initial estimation for a long time, you get some probability, and then you set your threshold to be lower than that, so that like all your support is on eigenspaces above this. You can do this, and it turns out to be that in some cases this is not good enough. And there's a slightly better way to run this that we got in later work, where what you do is actually you run the adversary once and check whether it succeeds. And then if you estimate the adversary success probability after you've observed it succeeding once, you kind of like de-weight all the bad subspaces, and you make this work with like probability 1. So there's several ways to handle it basically, but I'm going to ignore it and just focus on like the main loop. Two questions at the same time, so one of you.
I guess my question is more big picture, especially what you said about the probability of like 1/2 and it being kind of superposition of the other probabilities. I think I'm sort of lost in everything that's been going on. So what exactly allows you to say that? Or is that just like a general truth about how you think about success probability?
Okay, so wait, the question was how do we. Sorry, I had a little trouble figuring out what the question was.
Well, you're looking at this, I guess what I think is like this overall success probability of like 1/2, and then you said, well, that could be a superposition of these other probabilities.
Yes.
What in this context allows you to kind of get there, and like what assumptions did you make, or is this like a general thing about success probabilities?
Right, okay, so everything you said sounded right. The point I was making was that there is like the actual success probability in the sense that like what is the probability you answer correctly on a random R. And then there is sort of like your like mathematical success probability or true success probability. I should have come up with a better word for this. But I'm thinking of your true success probability as like your eigenvalue when you look at this Jordan decomposition. And I'm saying that there is a distinction between these two, that you could have if you have like a certain true success probability, if your eigenvalue is p, then your actual success probability will also be p, but it doesn't go the other way. Right? That p could arise from being a superposition of different true success probabilities that just happen to average out to a certain value. Okay, so but what we want to work with is like your true success probability, not your average one, right? And the way we get a handle on your true success probability is by running this estimator. Like this estimator actually, like after it's done running, really collapses you to a particular like true success probability. Like after it's done and it's estimated that your success probability is, let's say, 1/4, like all the components that are inconsistent with 1/4 have been like massively de-weighted. Like all that survives is the component of the adversary that's consistent with like 1/4 success probability. So like this procedure is how we sort of bridge the gap between like your average success probability and your true success probability, in that like, we can start from a superposition of different success probabilities, and running the Marriott-Waters estimator will collapse you to one of them. Does that make sense? Like, and then we're trying to sort of say that we're restoring you back to a particular like true success probability of p.
Can I think about this in terms of like weighted events, or is that like totally off?
I think the most helpful way to think of it is just that each success probability is its own like linear subspace. And we can basically, like, these quantum algorithms allow us to move a state into a particular linear subspace. They can't move me to like just satisfying some arbitrary abstract property. So I'm identifying linear subspaces that like very closely correspond with success probability and saying, well, I'm going to do something at the beginning to put you in a subspace where everything in the subspace has the same success probability p. And every time the procedure like bumps you out of the subspace, I'm going to try to move you back to that subspace. So that's the real distinction between like average success probabilities and true success probabilities. That true success probabilities are characterized as like corresponding to a subspace. And that is something that we can get a handle on. I cannot restore you back to some average success probability because that's not a subspace. Does that help at all?
Yeah.
Okay. Yeah.
I was wondering if you could go over like how MWP is projected.
Sorry, the fan's really loud behind me. I didn't catch that.
Could you go over how MWP is projected again?
Good. OK, so yes, I recognize there's I said a lot of things about two very, very similar procedures. So yeah, so let me go back just to make sure there's no confusion about this. So MW is the procedure that outputs a float between 0 and 1, right? This is just outputting some estimate. And I was claiming that MW is the procedure whose outcomes look like a projective measurement, in the sense that if I run it twice, I'll get two outcomes that are reasonably close with extremely high probability. Okay? Now, for my repair procedure, it's not enough to think about this Marriott-Waters procedure that outputs some arbitrary value between 0 and 1. I really want something that just says, like, am I good enough or am I not? So I define this binary version, this threshold version, like MWP, right? And this is run the Marriott-Waters estimator and output 1 if the estimate is at least p. And I'm saying this MWP is the thing that really should be a projective measurement for this template, right? Because these were supposed to be projections alternating back and forth when I analyze the termination. And this threshold version is very far from being a projection, even in its output behavior. And the reason for that is if you think about something, let's say, has eigenvalue exactly p, and the threshold is, and what this MWP is doing is saying, like, am I above p or below p, right? Like, if I have like a coin that lands on heads with probability like 0.279, and I flip a coin a million times, and I ask, like, is my estimate above or below 0.279? It could land on either side of that, right? It would be like probably 1/2. And I don't have any guarantee that if I repeat this, it'll make it any better. Right? So if I have two consecutive outcomes that are like 1/2 chance of being different binary outcomes, it's really not a projection. Okay. They're all really good questions. Anything more? Okay, so we were at this point where we were saying that our goal is to restore this invariant of being strongly p successful, right? Having all have your state be supported on the subspaces where your eigenvalue is high, at least p. And we had this problem where this MWP is not a projection. So there is a sort of a trivial way to fix this. Which is just you can take any quantum operation, any quantum measurement, and just make it a projection by expanding the Hilbert space. So I can just introduce new registers if I want. So I'll introduce these new W registers. So these will be some purifying registers. And the claim is that MWP can be implemented as some projective measurement pi p star on this larger Hilbert space. So previously, MWP was only acting on A, the adversary's state. But now I'm going to write it as a projection, and that means I'm going to have to add some extra registers. Okay? So maybe this works. Maybe I can just do that. Well, there's one issue comes up now, which is that now I've sort of destroyed the meaning of pi p star. Or I've destroyed the meaning of, like, I wanted this last step where pi p star accepts to certify that my adversary state is now highly successful. But in introducing these new registers, these new W registers, I have kind of destroyed this correspondence a little bit. Right? In particular, if this procedure has somehow has tampered with these W registers, if they're not zeros, then this measurement accepting doesn't mean anything. Right? Pi p star only corresponds to MWP when run on states that have 0 on the ancilla. Right? It has, there's no guarantees on its behavior when the ancilla is not 0. And you can actually check that when you run this back and forth, the ancillas will not be 0. So this is not like a made-up concern, that actually ancillas are non-zero. And so it's unclear whether you can trust this measurement. Right? If I'm computing the estimate of your success probability onto some register, and let's say I'm like adding a value to that register, and that register already has something written on it, I can't trust the estimate I get at the end. So how do I know that when pi p star accepts, that my state is actually good? So does the question make sense? That we kind of like faked our way to getting projections, and that's come back to bite us. Because by doing that, we've destroyed the meaning of these measurements. Okay. So indeed, this doesn't work. Like this, we don't have a proof that this works. The thing that does work is to modify the definition of the other measurement, pi r. So when you introduce this extra ancilla, we had a choice to make. Basically, these two measurements need to be acting on the same space. And so what should pi r do on these ancilla registers? You might think, well, it shouldn't care about them. Right? This is just the measurement that like checks whether you answered correctly on challenge r. It doesn't care about the ancillas you're using to estimate success probability. But it turns out the right thing to do is to redefine pi r to also project the ancilla registers onto 0. Okay. And so each measurement of pi r star is, like, morally, it's attempting to reset the ancillas back to 0. Okay. Right, so Chris, to your question, like last time, like, it took us a very long time to figure out that this was the right choice of pi r star, and I don't know how we could have really sped up that process except by the just sort of looking at the Jordan subspaces and thinking, like, what makes the analysis work. But yeah, I mean, this is kind of reminiscent of what we were doing all along, where we kind of want like one projector to like enforce something about the other measurement. But I don't have anything more precise than that other than we can analyze this. All right, so this is essentially the full repair procedure. You alternate these things back and forth until pi p star accepts. And one more comment, actually, is that the way this works, you might think that what you have to do is only terminate when you get 2 consecutive accepts, basically pi r star accepting followed by pi p star accepting. Right? You might think that that's what you have to do because pi r star accepting will first guarantee that your ancilla is 0, and then that guarantees that the subsequent pi p star is meaningful, right? That it actually corresponds to running the Marriott-Watchers estimator. But it turns out you don't actually need to do that. You can just, even if the previous pi r star rejected, this pi p star accepting is still meaningful. The state is actually still repaired. Yeah?
That actually calls back to a question we got from a previous talk, which is pi 0. Is it the same case when you do the measurement of pi 0 back in the previous talk, you don't care about the outcome?
Exactly,
You
yes.
don't actually,
It's analogous, yes.
and I guess it doesn't matter, but is pi 0 pretty likely to reject, more likely to reject than accept? Or I could get a handle on how likely it is that your
It really depends on the setting. Yeah, it's actually, if it were very unlikely, this wouldn't work. Like, this actually only works because there's like some entropy in these outcomes. So it's reasonably likely. Like, you actually, sorry.
Obviously, very close to half or something.
No. So you actually could run a version of this where you just wait until both of them accept in a row, and that might be easier to analyze. It takes longer to get there, and you could have like a different or more like naive analysis for that. But you actually can analyze this without having pi0 accept first, just like last time. Okay. So yeah, why does this choice of pi r star make repair work? It's not too different from what we did last time, actually, if you're able to like zoom out and look at this at the right level of abstraction. Right? The point is that when you define pi r star this way to project the ancillas onto 0, you're able to interpret the Jordan subspaces of these projectors. Remember, these are like a totally different set of projectors than the ones we've been looking at for the rest of this talk, like pi unif and pi accept. These are the projectors we're alternating to repair this state. Right? And when you look at the Jordan subspaces for these projectors, having pi r star project onto 0 allows us to interpret pi p star in terms of the Marriott-Waters procedure. So the claim is that if we start at s prime 0, which is a state that's in the image of pi r star, so I'm just saying because pi r star projects the ancillas onto 0, any state in its image has to have the ancillas being 0. Psi is a state that you would get to in pi p star if you alternate these back and forth until pi p star accepted. Right? You're guaranteed to be at this state if you're in the 2D subspace. Okay? So I want to understand this state. Like, this is the state that my repair procedure would output if I started here. Right? So why is this a repaired adversary? This is a question. Make sense? That like, this is where I'm starting from after I've damaged my state. If I were in this 2D subspace, I would be outputting this state, but on the A register. I would trace out the W. And I want to understand why is this like a strongly p minus epsilon successful adversary. And the proof sketch, so this is maybe the most like technical part of it, is you need to think about this almost projective guarantee of the Marriott-Waters procedure that says that if I run Marriott-Waters estimator twice on S prime, this bad event, the event that two estimates are more than epsilon apart, happens with at most delta probability. Okay? Now, what is this state psi? This state psi, you should think of as corresponding to the state after running Marriott-Waters once and conditioning on getting an estimate that is at least p. Like, that's what it means to be in pi p star. It means that I ran the Marriott-Waters procedure, or that's what it means to be in pi p star after my initial ancillas were 0. It means that I ran the Marriott-Waters procedure and I saw that my estimate was at least p. And moreover, the probability I saw that the probability this event happened, one second, is gamma, is precisely cosine squared of this angle here. Okay? So again, I know something happens if I run the Marriott-Waters estimator twice on S prime. Psi A corresponds to the state after running it once. And so I have some handle on what's going to happen when I run it one more time. In particular, this conditioning can only blow up the probability of a bad event by so much. So I'm conditioning on an event that happens with probability gamma. And so this bad event of getting two estimates that are more than epsilon apart is at most delta over gamma now. It only blows it up by a 1 over gamma factor at most. If it were any higher than this, it would violate my initial guarantee on almost projectivity. So the second event, the second estimate, in particular, the result of estimating the success probability of psi, is going to be at least p minus epsilon with at least 1 minus delta over gamma probability. So why p minus epsilon? It's because the previous one was p. And so if I'm within epsilon of that, I'm at least p minus epsilon in success probability. Okay. So I think this argument is like fairly involved, or at least takes a few minutes of thought. So don't worry if it doesn't make sense. I just wanted to show it in case anyone is curious of how we actually interpret these Jordan subspaces, or why this pi r star definition is important. Right? It allows us to think about the Marriott-Watrous procedure and then invoke these almost protective guarantees to reason about this particular state. Okay? And in particular, like if this state has the property that the Marriott-Watrous estimator is very likely to output an estimate at least p minus epsilon, it means that the weight of the state has to be on the high success probability eigenspaces. Okay, so I'll take maybe a question or two on this one. I know this slide has a lot of content, so I have about 10 minutes, right? Okay, and this is the end of the technical content, so. Right, have I lost everyone on this one? Thumb middle, up? 2 thumbs up? What? It's saying, like, but it's not really that I've controlled the future. It's that I actually knew something about that first one, right? That first estimate was going to be at least p with probability gamma. So I kind of knew everything that was going to happen to an extent. But one last thing is that you do have to rule out a bad case, which is you need to make sure gamma is not too small. Because if gamma is really tiny, then this is a useless bound. But what you can show is that what's really happening is, remember that we started out in pi p star, right? We start with something that is like strongly p successful. And we went from pi p star, we've basically forced the state onto pi r star, right? Or we defined pi r star so that would be like the state you ended up at. Like we transitioned from here to here. And if you imagine like, having a superposition across the different eigenspaces, and you force that transition, the subspaces where this angle is very close to 90 degrees get almost entirely deweighted. So I'm saying the initial disturbance causes you to like deweight the components on the subspaces where gamma is really small. So like on average, you can show that these gammas are actually not that small because of this initial deweighting that happens. And that's why you can say that, that this guarantee is actually useful. No, it has a slight dependence on delta because I'm lying a tiny bit. The initial state is actually not exactly in pi p star, just because if I ran pi p star on my initial state, it would only accept with probability like 1 minus some delta probability. So it's not exactly there. And so there are delta dependencies that show up.
But still sufficient.
Yeah. Yeah, one last remark, by the way, is that because you're going to run this many, many times, like you keep destroying the state, repairing it, destroying, repairing it, you don't actually want this multiplicative gamma factor to keep multiplying. That might be bad. And so there's this extra subroutine where after you repair the state, you estimate the success probability one more time to reset the failure probability to delta. So what happens is you pick up some abort probability here that's like negligibly small, but it causes it to like not multiply. So no worries if that didn't make sense, but there's a little bit more to it than what I'm putting on this slide, unfortunately. Okay, so let me just recap the high-level idea. So in the full procedure, you take the initial adversary, you run the Marriott-Watrous estimator, and you obtain some success probability p. And the effect of this is to concentrate the adversary's state on the subspaces where the success probability is really close to p, and deweight all the other components. Now, this is basically a linear subspace, right? You consider the span of all these eigenspaces really close to p. Like, that is a subspace that contains your adversary's state. And then the rest of this procedure is about trying to return to this subspace. So you have this one in the subspace of like p minus epsilon successful adversaries. You disturb it, or in particular, when you disturb it, you measure this bit, but actually also measure more if it's accepting. Then you repair it by initializing this extra ancilla, alternating these measurements back and forth, and then discarding the ancilla. And the argument we just gave said that this adversary is reasonably successful again. And it turns out the guarantee degrades a little bit from step to step. So you lose a little epsilon every time. But in this protocol, you know how many rewinds you want, or how many, you know how many accepting transcripts you want. So you can set epsilon in advance. So by doing this, by setting epsilon in advance, you can make sure that you never dip below the success probability you need. And so when you do this, each time you get a little bit of the PCP, and by the end, you're going to have either a whole PCP or a collision in your hash function. Okay. So where does this leave us? Here we showed this general procedure that whenever you have a protocol that satisfies this collapsing property, that you can basically rewind it as many times as you want and record the answers every time. So this gives you post-quantum soundness of Killian's protocol. And even for protocols that don't require a lot of rewinding, this technique where you don't lose success probability gives you much tighter analysis for protocols where you only need to, say, rewind once, like Blum's protocol. So for Blum, for instance, this gives you the optimal soundness error. It says that actually any quantum adversary who's convincing the prover with probability slightly bigger than 1/2, or noticeably bigger than 1/2, gives you an extractor that succeeds at probability close to 1. So it matches the classical setting. And so indeed, like, these protocols are not any less secure if you have the right post-quantum definitions. Since this paper came out, there's been many other applications. So it's nice work of Nir Batansky, Zvika Brikersky, and Yael Kalai showed advice-preserving non-interactive quantum reduction. So they're looking at the setting where you have quantum adversaries on even like non-interactive cryptographic primitives, but you want reductions that don't have to clone the adversary's advice. So if I have like a single adversary that does something for me, how do I use it multiple times? And they use this technique to basically extend a lot of classical security reductions to handle this case where you don't need to, where you can make use of a single copy of the adversary. With Alex Lombardi and Nick Spooner, we use these techniques to do post-quantum zero knowledge. So Watrous' result handles some class of zero knowledge protocols, but doesn't capture a lot of different ones. So for instance, I think one of the original zero knowledge papers had a protocol for graph isomorphism and graph non-isomorphism. And Watrous' technique handles graph isomorphism, but doesn't handle graph non-isomorphism. And so the post-quantum zero knowledge of that was open for a while. And the problem with graph non-isomorphism is that there's a part where you need to extract a lot of transcripts from the verifier. And so you can show that using this technique, you can prove the post-quantum zero knowledge of graph non-isomorphism. So we did that, as well as several other protocols. Another work of Russell Lai, Julia Malavolta, and Nick Spooner, they applied this technique to practical protocols. They showed that a lattice-based version of bulletproofs, which has many, many rounds that rewinding happens across, not just this single-shot rewinding where you're only rewinding the same 2 messages every time. They showed how to extend this technique to these many round protocols that actually have practical implications. In this upcoming work with Sam Gunn and Nathan Ju, who are in the audience, and Mark Sandry, we do quantum communication succinct arguments, as well as several other things. And we get this from assumptions that are weaker than one-way functions. So computational assumptions still, but because they're quantum, they can be potentially weaker than one-way functions. And the way we prove security is through this technique. All right. So thanks for your attention. That's all I want to cover.